Hi everyone, and welcome back to another video in the online lecture series of Database Design and Implementation course. So this is the part 2 of the part 2 video of our continuation on chapter 2, which is data models. So if you remember, in the last video, we discussed about the importance of data model and data modeling, and what is the purpose of using data models within the context of designing a database. Okay, and thereafter we discussed some of the important building blocks of a data model and looked at some examples, and then we took or discussed what business rules are and how to transform the business rules into the data model representations. So in the part 2 of this video, please make sure that if you have not watched the previous video, to go back and learn about them before you jump into this particular lecture, right? So this video lecture is going to discuss the remaining two topics of chapter 2, which is the evolution of data models and the degrees of data abstraction. Okay, so our discussion with the evolution of data models is going to be a bit of a brief overview, where we will talk about the different components and the different features or properties of the data models and how it has evolved from the early days, that is around the 1960s, to the present generation. Okay, and the degrees of data abstractions are basically some of the steps that you have to follow when you're trying to create a good database design. Okay, and what are the different submodels that are involved in that process. So we'll say part 2. Okay, so the first topic that we have in part 2 is basically the evolution of data models. Okay, so early days, when we were in the 1960s and 1970s, we had the computerized file systems. Okay, and thereafter in the 1970s, we had the very first data models. Right, and these two were known as the hierarchical data model and the network data model. A quick note is that even the lunar missions, the moon landing one, which was around 69, okay, used these data models, okay, the hierarchical data models, in order to implement the data storage capabilities that were used for these missions, right? So you can understand how valuable they were in terms of data storage and processing. Thereafter, from around 75 to even current, right, we had the relational model. And it is one of the most important data models for database design, even in these days, right? Although there has been a slow shift towards more advanced data models that is kind of more suitable towards the current nature of the data trends that we are having with respect to big data, if you have heard about that buzzword term. But there are still many applications that has been already written or designed using the relational model, which is known as legacy system or legacy softwares, which is still using the relational model up until this day. Okay. Thereafter, around 1976, came the entity relationship model, which in short is also called the ERM. Okay. And then we had around 1985 to present, we had the semantic model, which kind of evolved into two different models later on. The first one was object-oriented, and the second one was the extended relational. Okay. So this is basically the nature of the evolution of different data models. So let's look at each of these models one by one, and then talk about some of their properties and features in brief. Okay. So the first one, the first ever data model that was established was the hierarchical data model. Okay. So the hierarchical data model, of course, the objective for all of these data models is to be able to manage a large volume of data, right? So the logical structure of data storage was an upside down tree. So I'm hoping all of you recall, if you have taken the data structure course before, that what is the representation of a tree. So instead of having the root node at the very top, you had the root node at the very bottom, and then you had different units. That was a representation of different entities that you're trying to store, or different data units. And then you had relationships between them, and it reaches to the single view of the data, which is the root node itself, right? So the properties that you have to keep in mind here is that each node had multiple child nodes. However, the difference was each child had a single parent node. So if you relate these two features together, you will realize that the relationship that could be implemented using this data model was mostly 1:m relationships. Only. Okay. There was no other way of implementing or any other relationship type. Okay. Thereafter, this data model evolved into what is known as the network model. And the network data model was an important stride in the evolution of data model. It helped us achieve two things. First of all, it of course improved upon the hierarchical data model structure, but it helps to establish M:(n) relationships. Okay, so that means this restriction that the hierarchical data model had, that it could only implement 1:m relationship, was first of all addressed by the network data model. So that means a given child node could have multiple parent nodes as well. So that was a very important stride going from the hierarchical data model to the network data model. Okay. The second thing that the network model helped to establish is established some data modeling standards. Okay, so it established standards such as what is a schema, what is a subschema, what is a data manipulation language, and then what is data definition language. I hope I'm left with space here. Okay. So this is also known as DML, and this is known as DDL. Okay. So schema is basically the blueprint of DB design. Or we can say blueprint of entire database. Okay. And this is basically a subcontext or a portion of database as seen by application developers. Okay, and this is as seen by database administrator or designer. Okay, and these are basically the language that are used for, so this is used for data transformation, and this one is used for database environment implementation. Okay. So after that, after the network model came what is known as the relational data model. And the reason behind that is people wanted more simplicity in terms of ways in which they can represent the storage and the functionality of their database, right? Hierarchical models and network models were all well and good, but it was kind of like a bit too low level, right? So you had to know the features of basically the software and the hardware platforms that you were trying to implement your database on in order for you to be able to represent or express your design. But as you know from the discussions of algorithms and in then implementing programs, if it is just a design or an algorithm that you're concerned with, you should not be bothered with the representation of the underlying platform on top of which you might, at a later date, implement your database. So that is the reason of the jump from network model towards relational data models. Is the goal was to seek to simplify the process of the representation of your database design. Right? So the relational model was built using or adopting the concepts of relations, okay, which is basically a mathematical concept that states that the intersection of a row and column, okay, so if you have a row and if you have a column, will be used to represent a particular data item. Okay, so that is what it is the fundamental idea behind the relational data model. Okay, and it is implemented using what is known as the relational database management software. Okay, so that comes also inbuilt with different DML and DDL techniques, and then the DML techniques use the help of relational algebra. That is what is powering its data transformation techniques capability. So relational algebra operates on the concept of relation in order to give you these strong and very robust data transformation techniques, which is implemented by the relational database management software. Okay, so the overall goal is simplicity, right? So that means it will hide or abstract all complex details from users. Okay, so thereafter, what database or what users will be concerned about is what data to store and what manipulations to perform. Okay, so basically the how part for these two topics was not of any concern. So it gave us the capability of a user interface, was provided with the relational DBMS. It also gave us a collection or a list of tables that will be implemented in the database, storing our data. And then finally, it gave us the very well-known SQL engine, which will help us with the manipulations. Okay, so that was typically your relational model. Now, as far as operation is concerned in the relational model, it did simplify some of the operations when compared to its predecessors, that is the network and the hierarchical model. Okay, but however, if you pay attention to all of these capabilities here, yes, the goal was simplicity, and it gave us techniques of the operational simplicity, right? You don't have to know the internal details of how things needs to be implemented and stuff like that, and you can focus on the what parts of what you actually want to store, what kind of manipulations you want to do. But there is still an essential feature that was missing from the relational model, is simplicity of the design illustrations, the representation of the design itself, right? So that led us to the next data model, which was the entity relationship model, okay, or the ERM. So the major goal here was simplicity in terms of representing the database design. That was its main motivation, right? So it gives us tools and techniques in order to achieve the same, right? So it gives us specific components, that is how to represent things such as entities, then attributes and then relationships. Okay, and then there are three different types of ER notation. So whenever you generate, so a quick note here, is DB design diagrams that you generated using ERM is called ER diagrams or ERD. And it uses a specific notation. So there are three different types of notations that are available to you. So the first one is known as the Chen notation, named after the person who developed it, who is after Peter Chen. Okay, and then you have the crow's foot notation, which is now the standard. And then you have the unified modeling languages, UML class diagram notation. Okay. So basically this is mostly used when you are doing some more of a object-oriented modeling in your data model, but you can also use it if you're trying to generate ERDs. But the standard way is mostly to use the crow's foot notation. So the thing to keep in mind is that if you had taken software engineering courses before this course, then you would be familiar with what modeling is. Okay, what unified modeling language is and what class diagram notations are and how you use that to represent a very big program, right? When you're trying to design the function calls and the flow of your program. Okay, so the same goes here as well, that you can represent the design of your databases by using different diagrams. So let's look at some of the ER notations. Okay, so ER notations. Okay. So the first one is so let's take an example first that we want to actually represent. So if we are taking the example of, we will just take the example from the textbooks, okay, rather than coming up with separate ones right now. So we will just look at first 1:m. 1:m relations. Okay, so in the Chen notation, entities are represented as rectangular boxes. Okay, and the relationship between the entities are labeled in diamond type shapes. So now if you're going to represent a 1:m relationship, let's say professor advises student, okay, and then you have 1 here and then m here. So this is basically a ER notation using the Chen type, the Chen's ER notation. This is a 1:m. So similarly, if you do 1:1, so if you have professor chairs a department, so this will be an example of 1:m. What is important for you to remember is rectangular boxes represent entities You write your relationship labels within these diamond boxes, and then you connect them, and on the connectors you specify your relationship type. Now a quick note here is that if you want to specify an attribute, then you will simply do it by pulling an arrow from here and then having an oval shape and then writing student name. Okay. So similarly, if you have more than one attribute, you will have another arrow from here, another oval, and then student ID, and so on and so forth. And you can continue it on both sides of your entity. And the same goes for m is to n as well. So I'm not going to delve into m is to n again. So if you have crow's foot notation, then the entities are again similar to the rectangular boxes, but a bit more lengthened. And then you have professor written here. And then the relationship with the other entity, whoops, couldn't make the straight line. So you have student here. And you don't use any kind of number values in order to represent the relationship or the relationship type. Okay. What you do is you use the representation of the crow's foot. So that is basically done like this. So one is represented by two solid lines, and then it goes straight here, and then it ends up as a crow's foot. So this is basically what a crow's foot looks like, apparently to the people who designed this notation. And then the label is written on top of the connector. And the attributes are written within this block. So you have student ID, and then you have student name, and then so on and so forth. Okay. So if you have 1:1, then your crow's foot notation would look something like professor, and then you will have two solid lines, and then two solid lines here, and then you have department. Okay, and then you can say chairs. Always read a representation from left to right, never from right to left. Whenever you see such a representation, you have to interpret it by reading the representation from the left to the right, and never the opposite way. Left to right, that's the way to go, right? So then if you have another example here, let's say student enrolls for courses. So you have student, and then courses, then you will have here a straight line, and then the crow's foot, and then a straight line and the crow's foot. Okay, so those are the three relationship types. So you don't specify the numerical value of your relationship type with crow's foot. Okay. And then if you have the UML notation, you again represent your entities using rectangular boxes. So you will have professor, and then you will have student, but each attribute will also have its own block. Okay, so that means here, once you write student ID, you will have to separate it from student name. Okay, and thereafter, when you draw the relationship label between them, you will have to say this is 1 to m, right? And you have to write advices here. And then you also have to write the bidirectionality of it. That is, to how many professors does a given student relate to or is advised by. That is going to be 1:1, and then you say advised by. So basically you have to express both the directions. Okay. So a given student always relates to a single professor in terms of being advised. You don't have a student having multiple advisors. Let's just assume that it is the organizational policy along those lines. And then a given professor can then advise multiple students as well. So both those relationship types are specified here. Okay, and the relationship label follows beneath them. So keep in mind that the most standard way is basically the crow's foot notation. So if there is anything that you need to be very familiar with, the first one is basically you need to know crow's foot. Chen's model a little bit, but not that often. And UML, you will see it very rarely, at least within the database design environment. Okay. So after that, we had the object-oriented data model. Okay. So which was also known as the OODM. So the main idea here is to introduce object-oriented properties to database design. So specifically, the introduction of the concept of classes. So classes is basically the way of introducing or implementing the different properties. So classes will help in abstraction and encapsulation, right? It will help to hide some of the non-essential details from others, right? And also, when we are saying object-oriented property, class hierarchy will help us implement the concept of inheritance. So if there is a set of particular attributes that is common across different entities, then if we introduce object-oriented design to database design, then we don't have to re-implement those attributes again and again, right? So typically, when we are talking about OODM, then we mostly use the UML notation in order to represent the OODM. So an example here would be, going by the book, that if we have, let's say, if you purchase something, so the example scenario that we are going to discuss here is if you make a purchase, you get a receipt, right? That receipt is also known as an invoice. So now if I want to represent the entity of invoice within my database design using an object representation within the UML notation, then I can have invoice as the name of the entity. Okay. And thereafter, I can have different attributes, and let's call it invoice number. Okay. NUMBER. Let's say invoice date and invoice total. Okay. And thereafter, I can encapsulate its relationship to different entities and then specify what is the relationship type with that entity. Okay. So we can have customers, and then we can have the line. Line is basically if you have a receipt, then you will have multiple lines in that receipt that will be listing the different products that you have bought. So even that line can be used as an entity to store the different data, which will list the different types of products that you have bought in that particular interaction. So what you're saying here is a given invoice will be associated to a single customer only, but a given invoice can have multiple lines. That means if you, as the user or the customer, you go and buy a product, right? It generates a receipt. So that receipt will only be associated to you, the customer. However, within that receipt, there could be m number of lines. That is, in a given visit, you can purchase multiple products. So that is what these two things are representing here, right? But in an encapsulated fashion or in an abstracted fashion. So that is the inclusion of object-oriented design. So now that you understand that, as a self-exercise, of course this is done in your book, but without looking at the book, there are three entities here. You have customer, you have line, and then you have invoice. Right? So try to represent this representation here using the UML notation and using the not ER notation but crow's foot diagram. Try to practice it. If you cannot, then look at the example in the book in order to see what the correct representation is. But the important thing is make sure that you understand. Okay. So thereafter, we had, I think this is 4. 1, 2, 3. Of course not 4. 5, 6. The sixth one. Did I number that? I did not. Okay. So that is why I forgot it. So the next one was object, relational, and XML, extensible markup language. Okay. So object relational is basically the merging of the flexibilities that the relational model introduced as well as the advantages that the object-oriented model introduced, right? So this gave rise to what is known as the O/R DBMSs, which had both the capabilities of the relational model as well as the object-oriented model. But the problem was this did not last too long, because at this point of time, when it came out, internet came into the picture, which gave a rise to a lot of unstructured data. And the representation of most of the web pages and the unstructured data was being done by using the XML format. So at that point of time, in order to be able to represent the design of storage of data that is using XML format, people had suggested the use of XML data models, okay, XML based DB. So that is what has happened. But later on, this kind of boiled down to the EERM model, or the enhanced entity relationship model. So what happens here is it incorporates the idea of attribute inheritance and abstraction, along with the concept of virtual entities for representation purposes only and not for implementation purposes. So to summarize all the traditional models, what we will be learning throughout the course of this semester is, first of all, for our data model, we will be learning about the relational model first. Okay, so that is the foundation of our database design. All the techniques in the form of schema, subschema, data manipulation language and data definition language will be established by the relational model. Thereafter, once the operational usage has been established, or which data model we are going to be used for the operational usage, we will use the entity relationship model built on top of the relational model for graphical simplicity of the representation of our database design. And then finally, on top of that, we will apply the extended entity relationship model in order to seek avenues of improvement in our database design by incorporating the concepts of attribute inheritance and abstraction, if applicable. Okay. So these two steps for your project as well is going to be mandatory. Okay. And for ERM, we will use crow's foot. Whereas this is optional. Optional in the sense applicable only if opportunity exists. Okay, so let's not call it optional, otherwise it will be misleading. If there is scope of applying extended or enhanced entity relationship model, which introduces the concept of object-oriented modeling, then you will have to apply it. Okay, so this is basically the summarization of the traditional data models. And after that, in the current generation, we have, let's put two more. So the final data model that we have is the big data, which uses basically the NoSQL models, right? These are mostly the newer ones, the current generations. Okay, just keep in mind that NoSQL does not stand for SQL is not present, but it basically is a representation of saying not only SQL. So it has more than that. So if you have heard about different data storage capabilities, such as, or different databases, such as MongoDB, you might have heard it, it uses Python, right? Or it is quite suitable with Python. And then if you have heard about Google's Big Table, and so on and so forth, right? So these are all different NoSQL data models. Okay. So the ultimate goal, since the volume of data and the velocity at which data is coming at you that you're trying to store is so high, the goal of NoSQL data model is to improve performance. With some trade-off in data consistency. Okay. So it will try to like compromise that for some period of time, the copies of the data that is stored in your database will be inconsistent. However, it is always available to your end users, given the nature of the high volume and the high demand that you have, right? So an interesting thing, or some interesting properties for these NoSQL models is the fact that, first and foremost, they're schemaless. So what that means that you don't have the concepts of tables or declaring tables and implementing them and then pushing data into them. You can just push data as they arrive based on a very specific universal implementation methodology, right? So for example, what MongoDB uses is a document-based database. So what that uses is a key value pair. So regardless of what data you are inserting, for whichever entity you are inserting, everything will be stored by a key value pair structure, right? So it doesn't matter if it is for entity professor or if it is for entity student. You don't have to define what is the entity, what are the attributes. You just insert the data and it will always use that universal storage structure, and then it will retrieve it based on that. The other thing is, and the reason why the performance is improved so much is because these are very highly distributed. Okay, they are not present in one single centralized location. You can break it down into smaller units and you can distribute them physically in different physical geographical regions such that it becomes closer to the location of the need of data, and then it can reduce the latency at which the data can be acquired from these data storages. Okay, so of course there are other properties which makes them, they are very highly fault tolerant, right? And they are scalable as well. There is only a limit to how much data you can insert in a relational database. After a certain point of time, it won't be able to perform that well when you compare it against these types of NoSQL databases, right? So if you take the database systems course on the graduate level, if you're interested, then maybe some of these topics will be covered in a bit more detail than this course, because this course is mostly focused towards how you design a database, which is the most important thing, and then it talks or focuses more on the legacy data model, which is the relational model, okay, and the ERM model. Okay, so a quick example of key value pair is that if you have a key value data model, okay, and remember this is a part of the NoSQL data model. And this is not only SQL. It's not like SQL is missing. It's SQL, and in addition to that, there are some other advantages, right? So key value storage would be something along the lines of you will have some ID, right? And you will have some key, and then you will have a value. So the value will have the actual data. The key will have the location of the data, of course. That's how key value pair works, if you remember that. And then you will have some numerical value to represent the ID number of that particular row. So whenever you try to extract some data, you will refer to it either by its ID number or the key if you know it, right? So if you use the key, the ID, then we'll see the location, find the address where the data is stored, and then it will extract the value and send it. So it doesn't matter what kind of data you're trying to store. Regardless, it will also always be in this representation. Okay. So as a self-study assignment, study the representation of key value data model and compare it with the traditional relational, not the traditional relational, but kind of sounds a bit redundant, with the relational model. Okay. So try that out. So the final topic from this chapter is basically the degrees of data abstraction. So any data model, to understand this, let's look at this. Any data model, when you're designing a database, can be broken down into four parts, four subcomponents. Okay. So the first component is known as the external model. The second component is known as the conceptual model. The third component is known as the internal model. And the fourth component is known as the physical model. Together, the external model and the conceptual model helps us with the representation of the conceptual design of the database. The internal model helps us to represent the logical design of the database. And then finally, the physical model helps us implement the physical design of the database. Okay, so this is basically the breakdown of a data model into its different subcomponents, and then how does that relate to the process of database design technique. So you remember in our earlier discussions we said first thing we're going to address conceptual design, then we're going to address logical design, and then finally physical design. So up until this point, everything above this is software and hardware independent. Everything above this is software dependent and hardware independent. And here you have hardware dependency. So again, to repeat the fact, in our course, we will talk mostly about the conceptual design and the logical design. So we will discuss in details about the external model and the conceptual model, and then the internal model. The physical model, we will talk about the activities that you can perform within the physical model, but we are not going to delve too deep into it, okay? Because it is mostly concerned with hardware mapping of our database servers that we will implement on actual physical platforms. Okay? So let's talk about the external model. So the external model is the representation of the database design with respect to a specific subcontext within the problem domain. Okay, so of course when we say representation, it's a graphical representation. Okay, so when we are doing that, so that means some of the subcontext can come from, let's say, the point of view of end users, the amount of information that they want to see from the database is not necessarily everything that you have in your database design. So we just want to show them a portion of what is relevant to them, right? So for example, if we are, let's say, talking about professors who will interact with the university database. So the professors will only be concerned about the students, right? They will concerned about the departmental activities, some of them, not all of them. They probably will also have, let's say, the information about the library and their own employee information. Their own personal records and stuff like that. Beyond that, if there is, let's say, entities like university resources, right? Legal affairs, then HR, then let's say finances, and so on and so forth. So this is something that does not concern this particular individual, right? So if you want to create a representation, a graphical representation to express the activities that is only relevant to an involved party of your database design, then what you end up creating is known as the external model. Okay, so that means within a database design environment, you can have multiple external models, right? Because you can have professors, then you can have students, then you can have executives within the university department. So they will be like dean or the provost or president, and then you can have staff, and then you can have external guests, and so on and so forth. So all of them will have their own external model. Okay, so basically the first thing that you have to do when you're designing your database is you have to identify what are the different involved parties within your problem domain who will be interacting with your database, right? So that is the first thing that you will have to identify. And once you have identified that, then you will model an external model for each one of those involved entities, right? So once that is done, the next step in the process is basically the conceptual model. So the conceptual model is basically the schema. So you can think of external model in terms of another terminology as the subschema, as we discussed it in the network model, from the networking model term. Whereas the conceptual model is the schema or blueprint of your entire database from the perspective of the database admin. Okay, so this is achieved by simply merging all external models. So remember the technique in algorithm design of divide and conquer, right? It is always easier if you break down your problems into smaller components and then merge them together in order to create the final solution. So that means if you are trying to develop the database design for an entire database, you don't directly jump into the final design or start bringing up the final design. You start with identifying the first step by identifying what are the different involved perspectives within your design process. And then you generate an external model, say EM1, EM2, up till, let's say, EMK, right? And then you merge all of these EM values together in order to create your conceptual model. Okay, and that will be the final representation of your entire database. Okay, so thereafter, if you're trying to implement it, the next step will be to develop the internal model. So here what you will do is here you will identify and select a software. Okay, with software basically implies which database management software are you going to use. And then once you do that, using the language or using the syntax and semantics of the selected DBMS, you express the implementation of your database environment. Okay, so this will involve, so if we are using the relational database management system, then this will involve specifying things like what is going to be the pseudocode in order to implement the entity, let's say professor, right? So if you are just using SQL, then you will have something along the lines of create table professor and then it will have professor ID, okay, integer, and then you have to specify the size, let's say 256, right? And then if there are any constraints to it. Next, you give professor name, and this will be a variable character of size, let's say 50 characters, and then any constraints. Okay, and this goes on, so on and so forth. Okay, with whatever you have, and then finally you close it. And then similarly, of course, there will be a semicolon. So then similarly, you will express all the other entities. So this is basically the part where you are highlighting the implementation. So from the graphical representation, you move into the implementation. And then finally, you have the physical model, which is basically the mapping of physical devices to your implementation code. So this mostly relates to fetching operation and storing operation. Remember, whenever you're writing a program and you write something along these lines, let's say C equals to A plus B, where A, B, C are simple variables, and then these are basic arithmetic operation, and this is an assignment operation. When this code gets executed, then the processor gives the instruction of where these variables are once it gets converted to its object code. And then that value is fetched. Operations are performed in the main memory, and then the result that needs to be stored goes to the location which has the label of variable C. Right? So that there are ways in which if you can specify the nature of the storage, then you can improve the performance by reducing the time it takes to fetch and store different data values which are generated during the manipulation. So physical model is basically expressing that in a very explicit way, right? So when you say that you want to manipulate the name of professors of a given professor, so let's say you want to change or modify. So I'm writing this in a very high level language. Modify professor name for professor with ID 2, something like this, right? So in your SQL query, you have to write something along the lines of select or not select, but basically update. It's an update statement. So you have to update it. So, but in the update statement, there is another clause that you will have to say. So update from where? Okay. So that is what you would want to change. Or if it is an entire table, then you would have to write something along the lines of alter, right? So you don't have to worry about the SQL syntaxes right now if you are not aware of it, right? But what you have to pay attention to right now from the discussions is that there are clauses where you have to specify where the data is coming from, right? And therein, you have the capability to specify the actual hardware drives where that tables are stored if you want to speed up the process of um, execution. So the thing to note here is that this is a very low level process. So as an implementer or as a developer, you need to be familiar with all the hardware locations that is trying to store the data and the directory or the path of how you want to access them. And then you will need to also have the heuristics in order to be able to map them to the specific software processes. So that is why we are not focusing on this as far as the scope of this course is concerned, right? So if you want to summarize this chapter now, and if you want to relate it, so let's say if you want to talk about the database design process. So this is an overview of the steps that you need to undertake, and this is important with respect to your project, because from this onwards your phase 1 will be assigned, right? So the first step that you have to do is to find a problem domain. The second step is data and requirement analysis. That is, what are the different policies, procedures, what are the storage requirements, what are the processing requirements, what are the management requirements, so on and so forth, right? So this is, in a real world, this will come from basically interviewing with the clients and the different entities that are involved within your organization. But for the sake of your project, you have to make this up, okay, because you don't have clients as such. Thereafter, you have to generate or outline business rules, okay, and then you have to transform business rules to a data model. And thereafter, you have to develop external models So this is kind of together, step 4 and 5, because when you're transforming business rules to a data model, you have to identify the external models one by one from the business rules and then generate the external models by identifying which data model you have. And the data models that we will be using for our purposes will be relational plus ERM plus EERM. Okay, so these are the three ones that we will use. And once we have this, you will generate the conceptual model, and then finally you will select your DBMS, which in this case is going to be relational DBMS, and implement internal model, and then thereafter optional is physical model. But we don't need this for this course. Although I say it optional in the generic notion of the design process, we don't need it for the sake of the project. Okay, the physical model. All right, and then finally you can implement data transformation and data management. Okay. So that is basically the generic steps that you will have to follow for a database design process. Okay, so that concludes this lecture. So in summary, we have discussed about the evolution of different data models and briefly looked at some of the properties of these different data models. And then we discussed about the different degrees of data abstraction, which in short means that what are the different models that you should undertake when you are trying to graphically represent your database design and thereafter implement it. And then we looked at some of the generic steps in this particular slide which are involved in the database design process for both its design as well as its implementation and thereafter management afterwards. Okay. So from the next lecture videos, the next 1 or 2 lecture videos, we will discuss about the components and the properties of the relational data model in a bit more in depth, and then we will follow it up with the ER data model and its representations. Okay, so I will see you all again in the next lecture videos. Until then, stay safe and take care.